how's it going, everybody? I am here on Thursday, April 15th, making this video. Today we're going to look at section 11.2, which means that we're going to be looking at series today. In our last section, we looked at sequences, which were ordered lists of numbers. Today we're going to look at series, which is just a sum of a sequence. It's a sum of that ordered list of numbers. So very, very closely related. One is the list, the other is the sum of the list. So today we're looking at the sums of those lists that we looked at in the previous section. We're going to want to answer pretty similar questions as we asked in the previous section. Things like, does the series converge or diverge? Just like we looked at, does the sequence converge or diverge last week? If it does converge, can we determine what it converges to? We're going to see, just like with our sequences, the answer is going to be sometimes we can answer that and sometimes we can't. If it diverges, in what way does it diverge? Are we tending off to infinity? Are we oscillating? Is there something else going on there? So types of divergence are also a thing that we might want to kind of classify here. So we're going to get started since this is our first day of looking at series. And again, we're going to talk sequences and series for the entire rest of the semester here. So this is very much our kind of establish our definitions and our notation kind of day here. We're going to start by looking at four series here that have some obvious and some non-obvious properties, just to kind of establish some things that we should be able to identify here. So here's the four series that we're going to look at. Remember, a series is a sum of a sequence of numbers. So here we can see that the first series that we're representing here is the sum of n, from n going from 1 to infinity. So this will be 1 plus 2 plus 3 plus 4 plus 5 off to infinity. It's the integers n. This sum right here just says add the number 1 for the number of times that are indicated by the bounds of the series right here. Starting from n equals 1, let n go off to infinity. Your nth term is always going to be 1. So this is the series that says 1 plus 1 plus 1 plus 1 forever. The next series that we'll look at is 1 over 2 to the n. So this will be all fractions with denominators that are powers of 2. So n being 1 says we'll start at 1/2 plus 1/4 plus 1/8 plus 1/16, and we'll add up all the fractions with powers of 2 in the denominator. And then finally, this guy over here is probably our most important one today, 1 over n. So this will be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. This is referred to as the harmonic series right here. It's something that we are going to kind of use as one of our most common basis of comparison here. So this will end up being one of our most valuable series right there, that 1 over n. So let's go ahead and take a look at the first one. These first couple are going to be really simple, but we want to use them to kind of establish some notation and see some not surprising things happen before we see our slightly weirder cases. So for this first series, the sum of n, and notice here, super short shorthand right here. If I just completely skip out on giving upper bounds, lower bounds on a summation, you can assume the standard bounds of starting at 1 and tending off towards infinity. If it was anything else, it needs to be notated. So this is sort of the default case is to sum from 1 to infinity. So this is the sum of n. For every series, we're going to want to consider two related sequences that are associated with that series. First, we're going to want to look at the sequence that's associated with the series in the sequence, which means that's just saying what are all the terms that we're going to end up adding up right here. So we can see that, so our notation for this is that a sub n is representing the terms in the series. On the other hand, s sub n is going to represent the sum of the first n terms in the series. So again, a sub n is a sequence that we looked at last class. I would indicate this is the sequence as created by the value n, and it's just going to look like our 1, 2, 3, 4 off to infinity out there. Our other very important sequence, though, come on, mouse, stick with me here today. Come on, you can do it. I swear you can do it. There we go. The sequence associated with the partial sum. So when I say a partial sum, you want to remember that all of these series that we're dealing with are infinite series. We're adding up an infinite number of terms. Partial sums are only going to look at the first part of the series. We're only going to look at the first n terms in that case. So here, for example, s sub 3 is the sum of the first 3 terms in the series, not the entire series itself, just the first 3 terms. So what we can see that we're doing here when we look at these partial sums, S1, S2, S3, come on, mouse, come on, you got to work, we got to be able to move around here, is that we can form a sequence of the partial sums, right? So what I can see here is we're going to get 1 and then 3 and then 6 and then the next one would be 10 and then 15. So notice that here what we're doing is we're forming a sequence where each term in the sequence is the sum of the first n terms of the baseline sequence, right? Our a sub n's right here. So this says if you add up the first 4 terms, you get 10. Therefore, down here, the fourth term is going to be 10. So the a sub n sequence is the individual terms. The s sub n sequence is the sum of the first a sub n's, first n a sub n terms right there. In this case, I think it's pretty obvious to kind of conclude some statements about these since we're obviously just adding up an infinite number of integers here. I think it's acceptable for me to say that if I let n get infinitely large, then the terms in this sequence are also going to get infinitely large, right? So just one term in itself, a single a sub n, as n gets infinitely large, the number itself is literally equal to what n is. So if n goes to infinity, then a sub n is going to go to infinity. The next thing I think I can say that I feel very comfortable about is that the sequence of partial sums is also going to tend off to infinity, and it's obviously going to grow even faster than the a sub n's were out here. I can see that here my fifth term is 15, as opposed to here my fifth term would just be 5. So my partial sums are getting infinitely large as n goes off to infinity, certainly, and they're doing so even more rapidly than the a sub n's were. Finally, I think I can therefore conclude that the series itself is going to tend off to infinity. I hope that's not terribly surprising. This says if you add up every positive integer, what do you get? Obviously, since there's an infinite number of positive integers, we're going to diverge off to positive infinity out there. So nothing too crazy, but we're kind of setting up some notation for ourselves here. So we're going to be dealing with both our a sub n's, the individual terms themselves, as well as our s sub n's, the sum of the first n terms in the sequence or series that we're considering. So now let's go ahead and compare this to the series, the sum of 1, right? Very simply stated right there, because there's no boundaries given. You know that it's going to be from 1 to infinity. Assume it's the infinite sum if you're not otherwise told. Here, what we're going to see is that each individual term, the a sub n's are the individual terms. All of the individual terms are just ones. Therefore, we see that the partial sums, S sub n, are going to be the sum of the first n terms here. So we're going to get things like 1, and then 1 plus 1 is 2, and then 1 plus 1 plus 1 is 3. All right, so no big surprises right here. It does look like in this case, though, if I say to you what happens to our individual terms as n gets infinitely large, and you should say, well, nothing really. They're just kind of hanging out right there. They're not getting themselves to be infinitely large or anything like that. The individual terms are staying at a value of 1 as n gets infinitely large. On the other hand, our sequence of partial sums is clearly getting infinitely large. The number of terms that we have is equal to that location in the sequence right there. And so it will be the case that our partial sums, as n gets infinitely large, will diverge off to infinity. And I hope that you all feel comfortable saying if you add up an infinite number of ones, you're going to get an infinitely large number out there. We're going to diverge off to positive infinity. So notice here, these are both really simple examples to get started with, but we've seen an example where the individual terms themselves get infinitely large, and therefore so do the partial sums. We saw an example where the individual terms themselves stay the same size, so these didn't diverge off to infinity, but still if you add up an infinite number of ones, you're going to diverge, and therefore we can still overall conclude the value or the convergence or divergence of the series itself right there. So those two weren't very exciting examples, but we want to kind of get this distinction between the a sub n's, the terms themselves, and the s sub n's, the partial sum of the first n terms, and get that notation out there. So now let's go ahead and look at the two that are actually the interesting ones that we actually want to consider here. These two actually matter, that we know kind of how to manage these. So this is the sum of the powers of 2 in the denominator right there. So we're adding up a bunch of fractions, and every fraction has the next power of 2 in its denominator. So real quickly, let's compare the things that we've seen so far. We've seen that the sum of the integers n had the features that every term in the sum was bigger than the term before it, right? Because we're doing 1 plus 2 plus 3 plus 4 plus 5. In the sum of the ones, every term in the sum was the same size as the term before it, because we were just adding up a bunch of ones. And both of these diverged off to infinity. Now we can very clearly see that in this example right here, every term in the sum is smaller than the terms that came before it. 1/2, 1/4, 1/8. And therefore, it seems plausible to me that maybe this sum converges. Is that the wrong? It's right there. It's at least more plausible than the first two examples. I think it's relatively obvious that these two are going to diverge right there since we're adding up an infinite number of integers. But now that we're adding up an infinite number of fractions where each one is smaller than the next, I'm thinking maybe this thing might actually converge. So what we should do is we should explore both the a sub n and the s sub n sequences here. So first things first, what do all of my terms look like? That's what we've got going on in this block right here. This is saying write out the first bunch of terms that you're going to see in the sequence or its associated series. And clearly here, since we're adding up the powers of 2, where n starts at 1, we're going to get exactly what I've verbalized. 1/2, 1/4, 1/8, 1/16, 1/32. These are all the terms that we're adding up in the series. This was the associated sequence right here. The next question is, so now that I know what a sub n looks like, my question is, what does s sub n look like? And even better, can I state it like pretty succinctly? And so here's what I'm seeing for s sub n. It looks like s sub n is going to have us adding up 1/2 for the first, so the sum of the first one term is 1/2. Then we add in 1/4, and we can see from some quick fraction math that a half plus a fourth is 3/4. Then if I take my 3/4 and add 1/8, that's like 6/8 plus 1/8 gives me 7/8. Now I know the first three terms are 7/8 plus 1/16. Well, that's like 14/16 plus 1/16 is 15/16. So it seems to me like I might want to say something like s sub n equals 1/2, 3/4, 7/8, 15/16. That's kind of what I've concluded from the little bit of arithmetic that I did right there is what does our general structure of the s sub n sequence looks like now. What I'm wondering is, can we come up with some formula for s sub n rather than explicitly stating exactly what we're actually getting at each of the terms? This is sort of my exhaustive list, but can I come up with a formula here for s sub n? It seems to me like in the denominator for s sub n, we keep on getting 2 to the n power, right? 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. That's what we're getting in the denominator. What I can also see is that the numerators are always 1 less than the denominator. So it seems like this is a reasonable formula to compute the partial sum of the first n fractional numbers where we get a denominator that's the next power of 2 out there. So my question for you then is, what happens as we let n tend off towards infinity? Well, that's a kind of easy question to answer right here. If I let n get infinitely large, then we should see that this subtraction by 1 is going to make an infinitely small contribution to that numerator right there as n gets bigger and bigger and bigger. It looks like the 2 to the n and the 2 to the n are clearly the dominant terms here. It seems to me like this limit is going to head to 1 right there, the limit of the partial sums. So what I want to do is sort of visualize how we might be able to make this conclusion right here that perhaps what I'm seeing is that maybe this infinite series maybe sums to 1. Let's see if we can kind of take a look at some ways to sort of visualize this. One thing we can do is, in this case right here, we can graphically visualize this sum right here. And here's the way I'm thinking about this. When we have n equals 1, I'm going to draw this on the number line. If I'm thinking that this series is going to converge to 1, let me back up that line a little bit right here. If I think that this is going to make this sum up to 1, then what I'm thinking I'm seeing here is that we're starting at 0, we think we're getting to 1, and what I'm seeing here is that when n is 1, that our sum took us to 1/2. So I'm kind of saying my solid line here is what we got. The dashed line here is what I assume that we're going to fill in by allowing n to tend off towards infinity. If I let n be equal to 2, then you should see that we not only got to 1/2, but we also, out of the halfway to go to get to 1, we also got the next half of the way there. So now this is another 1/4 right there, and that got us out to 3/4. Right? So maybe instead of putting that 1/2 on the top of the bar, I should be putting this thing like right there. All right, and we still are missing a remaining chunk right there. And then we let n go to 3. And in this case here, the 1/2 gets us the first half. Then out of what's remaining to get to 1, 1/4 takes us half the way there. There's a 1/4. Then to add on 1/8, well, 1/8 is going to take us again half of the rest of the way to 1, right? So every time we add in a new term, it takes us half of the rest of the way to 1. I think I can also say since no term will take us all the way to 1, I can say the series is bounded by 1, or I should say the sequence of partial sums is bounded by 1. All right. Now, what's the nice thing that we learned in our last video? Well, the thing that I learned in the last video is if we have a sequence, like I have a sequence of partial sums, and if I know that it is both bounded and if I also know that it is monotonic, then I'm guaranteed that it converges. So by the monotonic bounded theorem, it must be the case that our partial sum sequence is going to converge. Our sequence of partial sums. So if we keep on adding on one new term, one new term, one new term, and we add up the terms up through those first n terms, we're going to see that that sequence is going to converge, right? So one, I kind of know this converges because I can see that it's bounded, I can see that it is monotone. Therefore, by our monotone bounded theorem, that sequence of partial sums is going to converge. Another way that I can think about how I know that this guy is going to converge is I can think about playing this as a game. So this is going to be an alternate way that we can visualize this, right? So what I said, one way we can visualize this sum is graphical. Another way is by playing a game. So here's the game I want to propose to you. Here's the game. This is a stupid game. Suppose we play a game, and here's the way the game works. You are going to flip a coin. And you're going to flip a coin. You're just going to keep on flipping until you flip a heads. If you flip a heads, then you've won. My question to you is, what is the probability that you eventually win the game? Right? I told you it was a stupid game. What I think that we can all come to an agreement is that our probability of an eventual win is going to be 1. I think it's guaranteed that if you sat and flipped that coin forever, that you are eventually going to get ahead. Obviously, we don't really anticipate it taking forever. A vast majority of people that play this game are going to be done in a few seconds of flipping the coin right there. But I think we're all hopefully comfortable with saying there's a 100% chance that you will eventually flip a heads if you flip a coin forever, right? So my question is, how might this happen? Well, you could win on the first flip, or you could win on second, or you could win on third. obviously, on and on and on. Now, I'm underlining the word or on purpose here because or is a very special probability word to us that says do some addition. So what I can do is I can do some addition between these independent events. These are independent events because coin flips are completely independent from one another. I don't care if you just flipped a coin and got 50 heads in a row, you're still a 50-50 chance of heads or tails on the next one. It's not like that probability has ever changed, right? So what I'm thinking to myself is that the probability should be 1, that they're associated with the probability that we win on the first flip, plus the probability that we win on second, plus the probability that we win on third, et cetera, right? We can just do that infinite sum of probabilities out there. And what is that actually going to look like to us? Well, this should be my probability of just getting a heads, right? If I'm going to win on the first flip, then that means that I just got a heads on the first flip. If I'm going to win on the second one, then that really means that it must be that I got a tails for the first flip and that I got a heads for the second flip. If I'm going to win on my third flip, it must be the case that I got a tails for the first, a tails for the second, and a heads for the third right there, right? And we could keep on playing that game out there as well. Now, what are all these probabilities going to be? Well, what's the probability of getting a heads? We know that to be 1/2. What's the probability of getting a tails then a heads? Well, that's going to be a 1/2 probability for the tails times a 1/2 probability for the heads. The probability that you flip a coin twice and get tails on the first and then heads on the second is going to be 1/4 because of the ordering of that matters here, right? This is saying I needed to get the tails first to lose the first and then get the heads the second to win on the second. So I could keep on doing things like this. What's the probability that we get 2 tails in a row? Well, that's 1/2 times 1/2. And then finally, what's the probability of getting the heads? That's going to be 1/2. And so I can keep on kind of writing out terms that look like this as well. And now we can see, what are these really? Well, this is just 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the fourth. I can see that this really is just the sum from n equals 1 to infinity of 1/2 to the n right there. So because I know that I will eventually flip a heads at some point if I flip a coin forever, that's how I know that this series converges to 1, which is really cool because this is an infinite series that we might otherwise kind of maybe struggle to see what's going to eventually happen with it. And thinking about this kind of dumb little coin flipping game here, just by knowing some basic probability facts, I can convince myself that this series is going to converge to 1. So here's the things that I'm seeing. 1, I can tell that the individual terms of this series, the individual terms of the series, this is no addition is happening here. What are the terms within the series? Remember that the a sub n is the individual terms themselves. So the a sub n's are 1/2, 1/4, 1/8, 1/16, the individual terms. Those are all clearly getting infinitely small. What happens as we take, this is really our limit as n goes to infinity of 1/2 to the n is equal to 0, right? The individual term is the 1/2 to the n, and that's going to get infinitely small. The next thing that we saw here is that if we take our limit of our sequence of partial sums, we did this guy up here, our sequence of partial sums, I think that we are all in agreement that if we let this sequence be constructed infinitely far out, then we're going to see that we're going to have these numbers converge on 1 because that difference of 1 from the numerator and the denominator is going to get to be negligibly small difference as the n values get infinitely large out there. So I hope that we're convinced that this partial series sequence is going to limit towards 1. And therefore, overall, I think we can conclude that the overall series itself is going to sum up to 1. All right? So that's good. So let's go ahead and let's take a look at our last basic example here, this series of 1/n. This is known as the harmonic series. This is a super important series. We're going to use this for lots of comparisons, this chapter here. This is sort of one of our series where we really, really want to for sure know about this one so that we can make lots of comparisons to lots of other series relative to this one. So, as usual, let's start by looking at our two related sequences, a sub n and s sub n, for the harmonic series here. The individual terms themselves, the a sub n's, all look like 1/n, where n is the index of the series. So 1/1, 1/2, 1/3, etc., right? So this is what our a sub n terms look like, the individual terms themselves. But that's just the sequence. We want to add up the sequence. So we can then say, well, if I start adding up the sequence, what kind of numbers do I get? Well, the first term is just 1. So S sub 1 is 1. It's what's the sum of the first one number. Then what's the sum of the first two numbers that we would get out of the sequence? 1 plus a half is clearly 3 halves, or 1.5. Then 1 plus a half plus a third, we're going to get 11 sixths. 1 plus a half plus a third plus a fourth, we're going to get 25 twelfths. So this doesn't seem to be like quite as clean as our previous example was. I guess the thing I'm saying is in the previous one, I did a little bit of math and I was like, huh, these seem to be all getting trapped below 1. And I don't feel like I can make a comparable statement that sounds like that here yet. Maybe we just need to look a little bit further though. So I'm not seeing any reasonable guess for a bound here. But we've only checked the sum of the first four terms. So let's have technology help us with a little bit of calculation here. So let's just pop over to Python real quick and see if we can kind of make some estimates of some bigger numbers here, right? Like, we're trying to talk about an infinite series. Only looking at adding together four terms is not really that robust of an exploration right there. So maybe let's have a computer add up many more terms of this for us, since the concept here is simple. I just don't want to do all the arithmetic. So let's pop over here and ask Python to do us a little bit of a favor here. So I'm going to go over here and I'm just going to write an ever so bare smidge of code right here. All I want to do is add up the first n terms in a sequence. So the way that I'm going to build this is I'm going to say, let's build a list. So that's why I've typed a bracket right here. And what do I want to be in the list? And here, let's do a thing here. I'm going to make capital N the number of terms that we're going out to. So I can do things like, first of all, let's just look at the first four terms here and see if they agree with the ones that we got in Microsoft Word. So the list that I want to build is the list that is going to look like 1 over n. Notice that's a lowercase n. For n in range, I want to start my values for n at 1. Where do I want my values to go up to? 4. The only tiny little wobble that I got to make right here is that the way that the range function works in Python is it always does include the lower bound, but it does not include the upper bound. So it's sort of like a bracket parenthesis is the way that range always works here. So I've got to do n plus 1 so that it actually goes up to just n right there. That's just a little technicality associated with that. That probably seems confusing and stupid, but there's really good, smart reasons for that. That was the right call on the Python developers' parts right there. But until you play around with the range function more, it's not obvious why. So what I want to know is what's the sum of this. So this is what I think I can call S sub n right here. It's the sum of, or excuse me, this is what I could call my A sub n right here. It's the first four terms. What we're going to want to do is we're going to want to add those guys up. So let's go ahead and see what A sub n looks like here. And in this case, we can see that we're getting the numbers here of 1, 1/2, 1/3, 1/4. So this does look like my appropriate A sub n sequence here. If I then wanted to see S sub n, I could just do the sum of the A sub n's. And what we were getting there in our previous was that S sub n was going to be like 2.0833, and we're seeing exactly that same term come up right here. So that at least tells me that the math I did by hand matches the math that I'm doing with the programming right here. So now let's go ahead and bump this up and let's look at many, many, many more terms. I don't think I'm going to want to see this A sub n because I'm going to do like thousands of terms here. So maybe let's just get rid of that and let's kind of bring these two terms up to just hang out with this guy right here. So I'm first going to build the list of terms themselves. That's the sequence. Then I'm going to add up the terms that I have in my finite sequence to get my partial sum right there, S sub n. And then I'm going to take a look and see what S sub n actually is. So just running this all in one block gives me that 2.0833. So let's go ahead and make this bigger. So what if I do the first 40 terms? Ooh, we're getting out to 4 now. What about the first 400 terms? Ooh, got us to like 6.5, first 4,000 terms. Ooh, we're up to 8.87. So it seems like I just keep on doing more terms and our number keeps on going up. So I'm kind of looking for this. I'm not even convinced that I could ever find what this does converge to if it converges, but I am thinking to myself, like, if this thing's going to converge, I should be able to make some sort of statement that's like, oh, it doesn't look like our numbers seem to be getting above 50 or something like that. And so far, I don't see any every time I've done 10 times as many terms, we just keep on getting a larger and larger number right here. So is this, ooh, that one took a second to run right there. Did you see that little pause? Watch now, this one's actually going to take a little moment to do the calculation here. It's thinking, it's thinking, it's thinking. Okay, so where are we even at right now? There's hundreds, thousands, so we're at 40 million. So by summing the first 40 million terms, we got out to 18.08. That's 40 million terms. Let's just change this to 100 million terms right there. And if I do the first 100 million terms, and it's got to think really, really, really hard right here. Oh man, is it thinking really, really hard right here? Okay, 18.9. Oh man, are we bounded above by 19? Well, let's look at the first billion terms and then we'll call it good here. All right, just double checking that this is a billion. Yes. Our first 1 billion terms. And boy, is it got to be doing a lot of thinking right there. It's making a list with a billion numbers in it, and then it's adding together a billion numbers. So Python's doing a lot of basic arithmetic right here. Um, Come on, I just want to see the number that we're going to get right here. It shouldn't have been that much longer. Wow, holy cow. It is taking a really long time here. Well, we did 100 million and we got 18.99. I just wanted to show that we certainly are going to get a number bigger than 19 for our 1 billion terms right here. But man, maybe Python's maybe there's some special memory limit that I'm not familiar with that we just kind of hit by bumping that up to a billion right there. So in any event, I think that I can kind of comfortably come back here and say I really don't see any upper bound forming right here. And I was already ready for our 100 million right here. We got about 18.99. So this is basically making me suspicious that our sum is going to diverge in this case right here. It kind of seems to me like every time I increase the number of terms that we're including in our partial sum, we keep on getting a larger and larger output on the back end out there. And so it doesn't seem to be like being bounded above by anything. So let's look at two ways that we can show that this sequence or that this series actually diverges right here. If we think that this actually is going to tend off towards infinity, then maybe we can do a little bit of math to show that that's going to happen here. Holy cow, this thing is still running. I'm going to kill that so it doesn't. I think we're just using up all my computer's memory here now. Okay, there we go. Got it to stop. All right, so there's two different ways that we can go about showing that this is actually a divergent series right here. That this series, if we sum up the infinite number of numbers of the form 1 over n, with all the positive integers being n, that we will actually get an infinitely large number. And that's quite sort of crazy, and you should notice that in our examples right there, we went up to 100 million terms, and we still were only at 19. And I'm claiming that if we were to tend off towards infinity, then we would actually get infinitely large. Sort of crazy that in the first 100 million we only made it to 19, but maybe now is also a good time for you to stop and realize that 100 million is not a very big number. If you want to think about big numbers, maybe think about things that are like 1 followed by 100 million zeros, or maybe like 10 to the power of 100 million. Or 100 million, I should say, to the power of 100 million. Now we're kind of maybe thinking about slightly larger numbers right there, and maybe it's more plausible to think that our series might continue to just be growing and growing and growing for all those out there, and we might be diverging. So there's two different strategies that I'm familiar with to show that this guy diverges right here. The book sets us up with one. I remember a slightly different one from when when I first was introduced to this, or I should say, when I was second introduced to this in graduate school here, since I definitely saw this in Calc 2. So let's go ahead and look at each of these two arguments that get made right here. So what we're going to do is we're going to suggest, well, if the harmonic series converges, it should converge to some number, so we'll call it h. So I'll call this 1 plus a half plus a third plus a fourth. And I'm going to need to write out kind of a bit right here because we're going to want to alter some of these terms to make a comparison series here. So I'm going to write this out to like 1/10. So what I want to do is I'm going to come up with a new series now. So this is the harmonic series. It's H. I certainly do have a plus dot 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 out there. So H stands for the harmonic series. G is going to be a nearby series. It's going to be a series that I'm going to make based on the harmonic series, but I'm going to make some adjustments. So here's the adjustments that I'm going to go ahead and make for myself. One, I'm going to leave the first two terms alone. I'm not going to do anything with these. 1 plus a half. What I want to do with my next terms now is I'm going to take this 1/3 and I'm going to make it a smidge smaller. I'm going to make 1/3 only 1/4, and I'm going to leave the 1/4 alone. So notice that 1/3 just became a smaller number of 1/4 in this comparison guy right here. Very similarly, I'm now going to do this for my next group of terms. Notice that 1 over 4 was a power of 2 in the denominator. I'm going to take my next grouping of terms and convert them all into our next power of 2. So I'm going to make 1/5 smaller and make it an eighth. I'm going to make 1/6 smaller and make it an eighth. 1/7 smaller and make it an eighth. And I'm going to leave 1/8 alone. All right. So we can see all three of those numbers in our series just got to be smaller numbers right there. And then my next term right here is going to be same thing out here, right? Then we're going to go something like 1/16 and 1/16 and 1/16 out there, and we're going to add up a whole bunch of terms that where we've made these numbers smaller until we get to actually where 1/16 is, then leave that guy alone. So what does our G sequence look like right now? Well, this now looks to me like 1 plus 1/2 plus 1/2 plus 4/8, that's 1/2, plus we're going to get 8/16, so that's going to be plus 1/2 right there. It seems to me that our series G is actually just going to be 1 plus, we're just going to add up 1/2 an infinite number of times, right? Now, I hope that you're all down with the fact that since we talked about the series of the sum of the number 1 an infinite number of times diverged, this one should just be half that size. Infinity divided by 2 is still going to be infinity. So it seems like it's got to be the case here that G diverges to infinity. And remember, our conversation here wasn't supposed to be about G, it was supposed to be about H. Well, how are G and H related? Well, I can very clearly see that for every single term by term comparison in their two series, either the terms in G and H are equal, or the term in G is less than the term in H. So I think I can say further, we can see by the adjustments made to create G that G is less than H. So this is like our comparison theorem right here, which we're going to deal a lot more with formally in about a week right here. So basically what I've concluded is that H, our harmonic series, must diverge because I changed some of the numbers into smaller numbers. I proved that that smaller numbered sequence obviously diverges to infinity because we're adding up the number 1/2 an infinite number of times. Since that smaller series diverged, the larger series H therefore must also certainly diverge since it has a bunch of numbers that are even bigger than the ones that were used in the sum for G. Now, the thing that's obviously a little bit weird right here is that we're sort of collapsing some of these onto each other, right? Here it took 4 terms for G to create one of the 1/2s. It's going to be 8 terms from G to create the next 1/2 and things like that. But here's the power of infinity. It's not like we're ever going to run out of terms. We're always going to be able to do this, and we clearly are getting an infinite number of 2's. It's certainly the case that we have collapsed several terms to being one term right here. We're never going to run out of terms. That's the whole point of this being an infinite series right here. All right. So there's another strategy that we can use that also uses so we sort of did some like specialty grouping right here to generate some numbers that were all equivalent to one another so we could write them as a much more simple series that we actually recognize. So we're going to do another thing that's like that. But I kind of like this one. I don't know. This is just a personal preference. There's no this is not a better or worse thing right here. I just like this better because I kind of like this proof by contradiction idea right here. So what a proof by contradiction is, we looked at a proof by induction in the last week. A proof by contradiction is a proving technique where you assume something to be true that you actually don't think is going to be true at all. Like I'm going to assume that the harmonic series converges. What I'm then going to do is I'm going to allow that sort of mystery statement that I actually wasn't that sure about, I'm going to let it lead me to a crazy place. And if it can lead me to a crazy enough place, I'm going to have to be able to say something like, well, it must be that my initial assumptions were wrong. Our harmonic series couldn't have possibly converged. Otherwise, we get this nonsense statement. Therefore, it must be the case that the harmonic series actually diverges. So in a proof by contradiction, you take the thing that you want to assume that you want to prove is true, and you assume it to be the opposite. We're going to assume it to be false. We think that we're proving that the harmonic series diverges. My step one for this proof by contradiction is going to say assume the harmonic series converges, and we're going to let that take us to somewhere crazy. So, proof by contradiction, we're going to assume that h equal to the sum from n equals 1 to infinity of 1 over n converges. And I'm saying converge. We sort of named this thing h, but I'm claiming that h is sort of like, we're assuming it converges, so h is the value of the convergence. It's the number that we converge to. So again, we're going to do some sort of like grouping thing like we did in the last one. So I'm going to go ahead and once again, I'm going to write out our first terms right here because again, I'm going to want to alter some of them and group some of them. Apparently I can't count with my integers here. Doing 1/3 twice, 1/4, 1/5, 1/6, 1/7, 1/8. And here's the way that I'm going to group these guys up. What I'm going to go ahead and do is I am going to go ahead and do a very, very similar thing as we did in the previous one, where I'm going to leave 1 alone. I'm going to leave 1/2 alone. I'm going to change 1/3 to 1/4, just like we did in the previous grouping, but I'm going to go a little bit different from here. So we're still going to do that as a fourth and a fourth. So you can see that we're clearly getting a half from this guy. For the next grouping, I'm going to turn 1/5 into 1/6. All right. For the next grouping, I'm going to turn 1/7 into 1/8. All right. So notice that all the adjustments that I'm making, once again, are making a smaller series than we had before. So now what I know is that whatever this series is, whatever it is out here, it's certainly going to be the fact that our harmonic series is bigger than that. Right? I know that the actual harmonic series is larger than this one. This stuff I just wrote out here is smaller because we took numbers like 1/3 and changed them to 1/4, a smaller number. 1/5 got changed to a smaller number, 1/6, stuff like that. So what is it that the harmonic series is actually bigger than? Well, it's bigger than 1 plus 1/2 plus 1/4 plus 1/4. That's going to be 1/2 plus 1/6 plus 1/6 is 2/6. That's 1/3. 1/8 plus 1/8 is 1/4. Hey, I feel like I recognize a bunch of these terms right here. It looks like what I can do here is I'm going to take this 1/2 and I'm going to put it over here out front, and I'm going to take this 1 and put it here, so it's kind of sort of like my starting location. 1/2 plus 1 plus 1/2 plus 1/3 plus 1/4. Well, it looks like all I'm really adding up here is another harmonic series. So it looks to me like the harmonic series must be larger than 1/2 plus the harmonic series? Well, that's insane. We're saying that the number h is larger than 1/2 plus the number h. That doesn't make any sense at all. That is literally an impossible statement. Um, that's impossible. Therefore, our initial assumption that h converges must have been incorrect. Thus, h diverges. Right? If it was going to converge, it would have converged to a number h, and that number h would be larger than h plus a half. And that literally doesn't make any sense. There's no number for which that is true. So in proofs by contradiction, you assume the opposite of what you're trying to show, and you let it take you to a crazy place. So your job with a proof by contradiction is to get to that crazy place where we can say, obviously, there's no possible way for this statement to be true. since we arrived at an impossible statement, it must be the case that we had an incorrect assumption that took us there. And then none of the arithmetic that I did was wrong. It therefore must have been our original assumption up top that must have been wrong. So it can't possibly the fact that that series converges, therefore that series diverges there. So I really like this proof by contradiction here. So I'll just say by contradiction is the proof style that I use to get there. I assumed it converged, and I showed that that is impossible, and therefore it must actually diverge, since that's the opposite there. All right, so there we go. So the harmonic series, we just did two different proofs proving that the harmonic series diverges, that the series of the sum of 1 over n clearly tends towards infinity. So all right. So, and that's not really that obvious. We're adding up fractions that ultimately, the millionth fraction is 1 divided by a million, right? I mean, we're adding up some very, very, very small terms, but because we're adding up an infinite number of them, it seems like we are going to get an infinitely large sum overall. But that's really not obvious because we just looked at the 1 over 2 to the n's. It's also the case that those were really, really small fractions we were adding up, and that converged, and it didn't just converge, it converged to the number 1, right? So that was a really, so those seem like they should be a little bit more related to that than that, and instead we got the values of their sums were 1 and infinity, which are kind of nowhere near to related to each other, right? So the point of this should be to you, sequences and series are tough. You can't just like look at it and be like, I feel like that one's going to converge. I feel like that one's going to diverge. You're going to be wrong like a lot. There's definitely lots of surprises that are happening underneath here. And so we want to be able to use some of these proving techniques to prove whether something converges or diverges rather than just kind of wonder about it. So let's go ahead and take a look at some of our theorems about series here. There's sort of 4 big statements that we want to make, and one of them will be associated with some computation that we can do rather than identifying some attributes of one of those series. So here's the 4 things that we want to state about series here. Thing number 1, and this is something that we've been doing today here. Let's bold these a little bit. Is that we have been kind of softly already using this first theorem right here. Given some series, the sum of the individual terms a sub n, we denote the nth partial series as s sub n, the sum up to, notice here, the sum goes up to n, not to infinity, and that's why we call that s sub n right there, because we're looking at the sum from the first n terms, 1 through n being the indices that are used of the a sub n's. If the sequence of partial sums converges to S, then the overall series also converges to S. We've kind of been softly in agreement with this so far. When we've made these statements, let me scroll all the way up and see where we've kind of said some of these things, saying, given, oh wait, we said that for a convergence statement right there, given that our partial sums, the sequence of partial sums converge to a number, it is therefore the case that the infinite series is going to converge, and it's going to converge to the same number. So this is like one of the kind of applications or agreements with that theorem that we just stated right there. If the limit as n goes to infinity of the sequence of partial sums, right? So what's the sum of the first 4 terms? What's the sum of the first 5 terms? What's the sum of the first 6 terms, right? That's our sequence of partial sums. If that converges to a number, then that will be the same number that the overall series also converges to. So that's our kind of our first statement right there. And I think that that's, this isn't a directly obvious statement. I think that the book does prove this one right here. But I feel like my intuition tells me that that's going to be true. If a series is convergent, then it's going to be the case that the size of the individual terms as you're going further and further and further out in the sequence that generates that series, those terms are going to have to converge on 0. This makes sense to me because if we were going to converge on anything else, like if we converged on 0.1 for the individual terms in the series, then eventually you're just adding up an infinite number of point ones, and that's going to diverge off to infinity. It has to be the case that the eventual contribution that you're making to the overall value of the sum is zero. Otherwise, the sum would then just be guaranteed to be getting infinitely large. Now, we should notice, very importantly, that the converse of this statement is not true. This is very much an if-then statement, and it does not go the other way. If we already know that a series converges, then you can intuit that it must be the case that the individual terms are getting infinitely small. It is not the case that if your terms are getting infinitely small, then your series is going to converge. That is not true. And we know this because we literally just looked at it. In our series or our sequence associated with 1 over n, it is definitely the case that our terms are getting infinitely small. If you let n go off to infinity, you're getting infinitely small contributions, but we just saw this guy diverged right there. So this statement backwards is not true. It matters that we interpret this statement only as an if-then and not an if and only if, meaning that it goes both ways right there. So it's got to be that this only works in one direction right here. And we can see in our harmonic, limit as n goes to infinity of 1 over n, the nth term is 0, but the sum diverges. Does not work backwards. Or I should say the converse statement is not true. Okay, that's what I literally did say right there. I don't need to write anything else. The converse is not true. If we flip this statement, then it no longer is true. So don't use this statement backwards here. If you already know that the series converges, you can conclude that it must be that the individual terms are getting infinitely small. If they weren't getting infinitely small, then they'd be staying finite in size, and you'd be getting a meaningful contribution from them, and that would result in the series being forced to diverge. Right? Third statement. If we get that there is no limit associated with the individual terms, if we can't show that the individual terms themselves converge on a value, or if they do converge to a number that's not zero, then our series is going to overall diverge out there. So if we can't find that the individual terms converge on something, or if they do converge on something and it's not zero, then we're going to diverge. I like to think about this case right here, and this is an oversimplification, but I like to think about an example of what we're referring to right here is if we're talking about things like the sine function, the sine of n, right? That will not have a well-defined limit since it's always just going to go up and down forever. It's never converging on any one value. This is like the example that I stated a moment ago. If it turns out that our individual terms are converging on the value of like 0.1, then in our series, we're adding up an infinite number of 0.1s, and that's going to diverge off to infinity. So there are multiple different types of divergence going on right here. This might be divergence by oscillation. This might be divergence due to tending off towards infinity right there. Multiple different possibilities for that divergence there, but if we find that we can't determine the limit for our individual terms, or if it's not equal to zero, then it's a guarantee that our series is going to diverge. So these are some limits that are useful for you to be able to show, being able to prove to me that a limit doesn't exist, being able to prove to me that you can evaluate a limit and you didn't get zero. That's helping you judge the convergence or divergence of a series right there. Finally, our last statement right here is a little bit different. These are all statements about determining features of a series. This fourth one is more about computation rather than proving a feature. The fourth statement is that we do get a known formula for computing the infinite sum of a special category of series. There is one special formation that series make, a geometric series, that some of them make, where if we can structure our series to be of the form of a geometric series, then we will be able to compute the number that it converges to. All right. In any geometric series, every pair of adjacent terms, I should say adjacent terms, has the same common ratio. And what I mean by common ratio here is if we take these two adjacent terms, and then these two adjacent terms, and then these two adjacent terms, and then these two adjacent terms, we can divide them all and we just keep on getting the same thing, right? AR over A versus AR squared over AR versus AR cubed over AR squared. All those are equal to R, the common ratio. Right, so we always get this by just looking at some a sub n plus 1 over a sub n in the series that's associated with that, which I guess I should say is distinct from the a's that are in here. I'll try not to introduce any variable confusion here. So what I want to know is if we do get something that looks like this, what's the sum going to be equal to? So this is our special structure, this a times r to the n minus 1. That's our special structure where if we can express a series like this, then it is a geometric series. Geometric series do have a known formula for computing exactly the value that they do converge to if they converge. So let's go ahead and see if we can do a little bit of the math that's going to get us there. So, 1. I know what my S sub n looks like, the partial sum of the first n terms. All right, what this is going to look like is it's going to look like A is this first term, plus AR is the second, plus AR squared is the third, plus AR cubed is the fourth, plus. Now you should notice that the cubed term is the fourth term, the squared term is the third term, the first order term is the second term, the zeroth order term is the first term. So we're always like off by one with what term we're looking at and what power we're looking at. So my question to you is, if we're only adding up the first n terms, then what's my final term going to look like in this guy out here? Well, it should look like something with an n minus 1 power, because that's the relationship that we've seen, right? AR to the n minus 1. Now, what I want to do for myself here is I'm going to say to myself, all these terms are almost identical to each other. They only differ by how much R stuff they have in them. So what I'm going to do is I'm going to create a second summation right here that's very closely related to the first, and I'm going to subtract the two of them to eliminate as many terms as I can. So what I'm going to do here is I'm going to look at R times S sub n. That's going to be AR plus AR squared plus AR cubed plus AR to the fourth plus all the way up to AR to the n, right? So all I did is multiplied our partial sum by R, and therefore I just stuck an extra factor of R onto all those guys. And so what I'm going to go ahead and do right now is I'm going to do a little bit of subtraction. Here I'm going to get S sub n minus R times S sub n. And you should notice that most of these terms are all going to drop off. This a sub r right here is going to cancel with this one, ar squared with this one, ar cubed with this one, ar to the fourth with this one right here. All the way to ar n minus 1 should be canceling with the term that's right before ar. It looks like the only terms that are surviving in this case are the very first a and the very final. Oh, I subtracted that, not plus. It's a minus right there since I subtracted it off. Should be minus ar to the n. And so now what I can see is I can get a formula for S sub n, because I could solve this guy for S sub n right here. So I'm going to factor out S sub n on the left. One minus r, and that's equal to a times 1 minus r to the n. And it looks like I can get at this formula here where S sub n equals a times 1 minus r to the n all over 1 minus r. Now, what I'm not so interested in here necessarily is the case that I want the formula for a partial sum of any geometric series. So this is our formula for the partial sum. Right, so that's one good formula here. But it's still the case that I didn't do this investigation to get a formula for a partial sum formula. I wanted the infinite sum formula when we add up an infinite number of terms. So that is practical. And if I said you find the sum of the first 50 terms of a geometric series, then you could just directly use this formula instead of doing the summation. But what I want to know is what's going to happen as we let this as we let n go to infinity. Um, let n go to infinity. So let's take our limit as n goes to infinity of this S sub n. That should be our limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. And you should notice that there's two different things that might end up happening here, right? So we're letting the number n get infinitely large. That means that we're going to take an infinitely large power on r. What I know is that that's going to pan out two different ways depending on the size of r, right? You should imagine for yourself, if r is like the number 2, then we're going to do 2 to the infinity power, and we're clearly going to get an infinitely large numerator, and it's going to diverge off to infinity. On the other hand, if r is something like 1/2, then we're taking an infinitely large power on 1/2, which is going to shrink it down to 0, which just means that we're just getting a as our overall numerator right here. So it seems to me to be the case is that if r is a number that's bigger than 1, then we're going to diverge off to infinity. If r is a number that's less than 1, then taking those large powers is actually going to crush us down to 0, and we're going to converge to some value based on the terms remaining in the series here. So we can state those two statements here. If the value of r, or its distance from 0, is greater than 1, then it's going to be the case that when we take this limit as n goes to infinity of a times 1 minus r to the n over 1 minus r, we're basically getting here a times 1 minus infinity over 1 minus r, which is going to diverge to infinity. On the other hand, if the size of r, our common ratio, is less than 1, then we're getting that the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r is just giving us a times 1 minus 0 over 1 minus r, and we're getting that this will then just be equal to a over 1 minus r. So this is kind of our conclusion for our infinite formula thing right here. If r is less than 1, then our geometric series value is literally just a over 1 minus r for the sum of the infinite number of terms that's right there. So for the infinite sum formula right here, you need to know that our common ratio needs to be less than 1, because otherwise our series is growing. The common ratio is what do you multiply by to get to the next term in the series. Well, if r is greater than 1, then the terms are getting bigger and bigger and bigger, and therefore we're going to diverge. If they're getting smaller and smaller and smaller, they're doing so multiplicatively rather than linearly like our harmonic series. So they're going to go to 1, they're going to go to 0 fast enough that we are going to in fact converge, whereas it seems like the harmonic series, those denominators weren't, our numbers weren't getting small fast enough, and we still were accumulating so much stuff that we diverged off to infinity out there. So now we got our two different formulas is what we built right here. These both only apply to geometric series. So remember, these only work out if you can somehow get your thing, your series, to be expressed like this. A times r to the n minus 1, where your sum starts at 1. If you can write a series like that, then it's geometric. And now we have formulas for both the partial sum, if you're going to do n terms, or the infinite sum, if you're going to do an infinite number of terms. We have formulas associated with each of these, and you know that the common ratio between them will help judge whether it will converge or diverge. So let's go ahead and look at some geometric series examples right here. So we can conclude that it's convergent if our common ratio is less than 1, and it will converge to a over 1 minus r. It is divergent if our common ratio is greater than 1, and it will go to plus or minus infinity right there. And I guess I actually want to say this should be a greater than or equal to. If your common ratio is equal to 1, then that just means that you're adding up an infinite number of the exact same term right there, right? That I would say multiply by 1 to get to your next term, then that would just be the sum of a. Right, that's going to diverge to infinity as well right there. So let's go ahead and look at a couple examples right here. The first example we should look at is we should recognize that that the series that we looked at a moment ago with our powers of 2 in the denominator, it can be written as a geometric series, right? So what I want is, I want to say, if this is geometric, then it should be written as the sum from n equals 1 to infinity of a times r to the n minus 1. That's the format we've got to be in right here. So I want to say, can I write this like that? Well, the first thing I'm thinking is I can rewrite this, and this is our sum. And remember, 1 to infinity is your default bounds. If they're not written, then it's 1 to infinity. And the first thing that I'm seeing here is I want this n to be an overall power on a term. So I'm going to think of this as 1/2 to the n instead of just 1 over 2 to the n right here. And what I'm seeing is this. It looks like right now, if I were to think of this as a number times a number to a power, the coefficient I have right here is just a 1 that we don't write, and then it's 1 over 2 to the n. What I need is I need this to be of the format n minus 1 to fit my geometric series formula. And so what I'm going to go ahead and do is I'm just going to go ahead and pick off one of those 1/2. And you should notice in this case right here, we now have a r to the n minus 1 right here, which is exactly the structure that we wanted to be in. And so remember now that this should be equal to a over 1 minus r. And so all I've got to do is just fill that out. A is our initial value of 1/2 right there, divided by 1 minus our common ratio is 1/2. That's just going to give me 1/2 over 1/2. And that's clearly equal to 1, which is exactly what we were getting in our examples up above right there. So it seems like this does agree with our infinite series formula right there, that a over 1 minus r formula right there. But notice we had to pull out our algebra sticks here and force this thing into a format that we wanted to be in. So you guys are definitely going to have to do a little bits of algebraic manipulations, especially with making your powers match up with what you expect them to be, to get all these things to line up for themselves right here. All right. So let's go ahead and look at another example. Let's find the sum of this series right here. And so it's not even clear that this is geometric, right? And if it's not, then we can't do it anyway, right? Geometric series are the only ones that we have a formula for. Geometric. Let's look for a common ratio. So what I'm always interested in doing is finding my ratio of two terms, right? If each of these represents an a sub n, an individual nth term in a sequence, then I want to do the ratio of two of them. So I'm going to get 2 over 3. I'm going to get 4/3 over 2, and that's going to be the same thing as 4 over 6, which is 2/3, right? Then I'm going to get 8/9 over 4/3. When I do this, I'm going to get 8/9 times 3 over 4. I'm going to cancel and get a 2, cancel, get a 3. I'm getting 2/3 from this guy. It looks like for all of the ones that I have available, they all have a common ratio of 2/3. And we started at 3, so we get that a is equal to 3. So I'm thinking to myself that when we write this series right here, that it should be the case that 3 plus 2 plus 4/3 plus 8/9 plus ... is going to be equal to, it looks like this is going to be our n equals 1 to infinity. We started at 3. We're going to multiply by 2/3 every time we get to a new term. So let's stop and convince ourselves that this is actually going to be legit here. When you plug in n equals 1, 1 minus 1 is 0. 2/3 to the 0 is 1. 3 times 1 is 3. So we got the first term. When we plug in n equals 2, we're going to get 3 times 2/3, which is going to give us 2. When we plug in n equals 3, we're going to square 2/3, so we're going to get 4/9. 4/9 times 3 is going to be 4/3 right here. So it seems like this formula is in complete agreement with the first terms of the sum that we'd found right there. All we had to do is ask what was the first number and what do you multiply by to get from one number to the next. If this didn't have this common ratio of 2/3 right here, then this wouldn't be geometric. The fact that I was able to just keep doing the division and keep getting that same number right there, that's how I know it was geometric. If that didn't happen, then it's not a geometric series, and we don't have a formula for that, right? So geometric series are special. They're like the ones that we can compute. So it looks like then our series value should just be equal to, and again, remembering that this is our a r to the n minus 1, that this is going to be a over 1 minus r. And when I go ahead and do that, in this case, it looks like I'm getting 3 over 1 minus 2/3, which is 3 over 1/3, which is going to be 9. Um, Great. So I think that we were able to determine the value that this series converged to by doing a little bit of exploratory division, not that hard, pretty basic math operation here, by seeing that we did get a common ratio by multiplication between each term and the next term. That tells us this is a geometric series. We identified the a and the r associated with that geometric series. We stopped after writing down the sum and recalculated and verified that we were in fact getting all of these terms. And then we just applied our very, very simple formula right there to get the value that this geometric series converges to. And again, I'm going to say it again. We only get to do this with geometric series. And if you can't write it in this format, then it's not geometric, and we don't have a formula to compute its sum. The geometric series are special like that. So, as our last question right here, let's look at something a little bit more generic. This is kind of leading us towards some of the stuff that we're going to see a little bit in some later sections here. For the series x to the n over 3 to the n, find the values of x for which the series converges. And when it does converge, find what it converges to associated with those x values right there. All right. So what I'm thinking to myself is that the only way that I can judge this is if this is, in fact, a geometric series. So let's see if we can write it that way. So the first thing that I'm seeing here is that I can certainly write this as x over 3 all to the n power. And I know that I want this in the form ar to the n minus 1. So the two things are, one, right now my a term is 1, but my power is n, which is no good. So I'm going to go ahead and pick off one of the x over 3's to reduce that power down to being n minus 1. So I'm going to get x over 3 times x over 3 to the n minus 1. This now does fit that form of a r to the n minus 1. So the claim now would be that this is going to have an a value of x over 3 and an r value also of x over 3. Those are the same term right there. We saw that geometric series converge when r is less than 1. We have the absolute value of x over 3 needs to be less than 1. That says to me that negative 1 is less than x over 3 is less than positive 1. And by doing some multiplication, negative 3 less than x less than 3 says converge if x is in the interval negative 3 to positive 3, not inclusive right there, right? Those are not equal to's right there. So for all other x values, this series will diverge. Now, an important thing for you to notice here is that in this case here, x is not really like the variable of consideration. The variable that this sum is all about is n, right? X is almost more like a parameter right here, where it's like, oh, if x was 9, it's not like x is changing over time right here. X is sort of like being treated as a constant relative to the sum. The n value is the value that is being controlled by the sum right there. So maybe it's even better to think about that x as, I don't know, we like to think of x as being like the independent variable that alters our future values here. I think it's better to think of that as like a parameter k or something like that. Something that we typically think of as like a constant that you can choose rather than a variable that determines our outcomes kind of thing, right? So what value does it converge to when it converges? So that is, if x is an element of negative 3 to 3, what does it converge to? Well, we can just do our simple little a over 1 minus r if it is converging. I know this is going to be x over 3 over 1 minus x over 3. And I'm going to just go ahead and multiply top and bottom, I think, by 3 over 3 right here, just to simplify this a little bit. Oop, oop, oop. And that's going to give me x over 3 minus x. So given that x is between -3 and +3, this series will converge to the value x over 3 minus x. So we can easily say things now like, if x is 2, then this sequence converges to 2, because that's going to be 2 over 3 minus 2, which is 2 over 1, which is 2. So we now have a general formula for what we converge to, given any value of x, and as long as x falls in that interval, it converges. If it falls outside that interval, it's going to diverge right there. Notice that if x was literally equal to 3, then we're getting 3 over 3 to the n. We're back to just our sum of the number 1, so it's an infinite number of 1s getting added up, obviously diverges. We can do these in general. What we've just found is a radius of convergence right here, and we're going to talk much more about those in coming sequences right here. This is our radius of convergence. So this is kind of an important topic right here. We're going to kind of regularly ask ourselves in the future. We're going to say things like, under what conditions does this series converge? And you're going to say, it converges if x is in the interval -3 to 3. That's your radius of convergence. It's the condition under which this is a convergent series. Identifying that radius of convergence is very useful for knowing when is a series going to converge on a desired thing versus when is it going to move away from that. That's going to be a really, really important feature for some of our conclusion topics at the end of this chapter 11 here. So this wraps it up here for me today for our introduction to series right here. What we can see is that we got we played around with some series a lot. I think the important things here was that we saw that we were interested in both looking at, in any series, we wanted to know what is the sequence of terms. We also wanted to know what is the sequence of partial sums. We looked at what's it look like when you add up the first 1 term, 2 terms, 3 terms, 4 terms. The reason why the sequence of partial sums is really valuable for us is because of our first theorem right here that says if the sequence of partial sums converges to a number, then the overall series itself also converges to that same number. So looking at our a sub n sequence and our s sub n sequence is very, very helpful in looking overall at our series information right here. So we got a couple theorems right here that aren't too crazy. We saw that we do get, there's a very special case of series, the geometric series, which most series are not. But if you do get a geometric series, it's one of the rare cases in which we know exactly when it converges and when it doesn't. And if it does converge, we can actually compute exactly what it converges to. And that's kind of rare out here. So these are some pretty special series right here. So being able to identify when something is geometric, really, really important, because we can do some pretty simple math. And notice the derivation of this formula is also really easy. I don't think any of us would have thought to do this on our own right here, but once you see me do it, it's like, oh yeah, I can totally see where those numbers came from. This formula kind of like fell right out right there. So not too bad of a derivation of that formula either. So that's going to go ahead and wrap it up for me today here for series. What we're going to see in the next video here is the fact that we should think of infinite sums as being closely related to integrals, since integrals are also adding up an infinite number of objects. And so what we're going to see is that we are going to get some close ties between integration and series here. So we're going to look in our next video at the integral test, which is going to help us determine if something converges or diverges. A series converges or diverges based on an integral. And we're also going to see how integrals can help us out in estimating the value of a series. So for series where they're not geometric, it's really tough for us to estimate what the series does converge to. Even if we prove it does converge, what it converges to is very difficult often to actually directly prove that it converges exactly to some number, but maybe we can get an estimate of what it converges to, and that's what another thing that we'll look at in our 11.3 video here. So I will see you guys in 11.3 for the integral test and estimation of sums. Have a good one.